There is an object racing away from us right now at over 40 kilometers per second. A silent speck of something hurtling into the blackness beyond Neptune. And the most unsettling part is that we have no idea what it truly is. It appeared without warning, a ghost in the celestial machine, behaving in ways that defy the textbooks, and now it is vanishing, leaving behind a trail of questions that challenge everything we think we know about our place in the cosmos. They named it 3I Atlas. The I stands for interstellar. This thing is not from here. It does not belong to our sun. It is just passing through. Except it isn't, is it? Because within weeks of its discovery in the summer of 2025, a deep unease began to settle over the astronomical community. This was no ordinary comet. It began to accelerate in ways that gravity alone could not explain. Its colour shifted, morphing from a pale, icy gleam to a disturbing ruddy hue as it dove toward the sun. Jets of material erupted from its surface, but they didn't behave like normal comet jets. Some of the gas was streaming toward the sun instead of away from it, an anti-tail jet defying the expected physics. Harvard scientists would later go on record saying it might be artificial. Internal NASA reports would quietly list 10 separate anomalies that didn't match any known comet or asteroid. And its trajectory, that is the most disturbing part of all. It didn't come here randomly. The path it followed, a precise arc along the plane of our solar system, suggests something more than blind chance. It suggests deliberate navigation, as if our little stellar neighbourhood were just another scheduled stop on an ancient galactic highway. If this object, this 3I Atlas, isn't here for us, if its purpose isn't to study humanity or make contact or deliver a warning, then the question that follows is impossible to ignore. A chilling whisper in the vast silence of space. What else is out there that it came to find? What destination could possibly be important enough to warrant a journey across the light years? We are about to embark on a journey of our own, a deep dive into one of the greatest mysteries of our time. We will look at the data, the hard science, and we will also dare to speculate, to ask the what-if questions that make some scientists uncomfortable. This is not a documentary that pretends to have all the answers. This is an investigation. So, let's start with the most basic question, the one that has launched 1,000 theories and more than a few nightmares. What is 3I Atlas? To understand that, we need to go back to the beginning, to the moment it was first spotted. Picture this, a silent visitor streaking through the inner solar system, its path carved across the blackness like a razor drawn over velvet. It was July 2025 when the Atlas Survey Network, designed to spot incoming asteroids that might threaten Earth, caught its first glimpse. Astronomers scrambled to catalogue its motion, its brightness, its trajectory. They gave it a name and quickly realised its origin was not from our solar system. This was only the third confirmed interstellar visitor ever found, but it would soon prove to be the strangest by far, because this object, this 3I Atlas, refused to follow the rules. It was an outlier from the start. As it approached the sun, the anomalies began to pile up. The non-gravitational acceleration, the strange nickel emissions with almost no iron, the extreme polarization of its light, the suspicious timing of its closest approach to the sun, a perfect window for a high-efficiency orbital maneuver. Each one of these quirks, taken alone, might be explained away. But when you stack them together, when you look at the cumulative weight of all these oddities, you start to wonder whether 3I Atlas is really a comet at all. Avi Loeb, a Harvard astrophysicist who has never been shy about controversial ideas, has publicly suggested that this object might be artificial. He points to the evidence, the pieces that don't fit. He's not saying it's definitely alien technology. He's saying we can't rule it out. And the scientific community is, predictably, split right down the middle. Clear about what we're doing here, we are going to explore both sides of this mystery with equal rigour. We'll look at the grounded science, the models and equations that suggest natural, if extraordinary, explanations. And we'll also indulge in the speculation, the what-ifs and maybes that emerge when the data simply refuses to behave. We'll talk about trajectories, about composition, about the possibility of intelligence, and about what it all means for us, sitting here on this blue marble, orbiting an ordinary star. Because if 3I Atlas isn't here for us, if it's not some cosmic messenger sent to make contact or warn us or study us, then the question becomes much, much stranger. Where is it going? What is it doing? And if there's any kind of purpose or design behind its journey, who or what set it on this path? We're going to break this mystery down piece by piece. In the first act, we'll lay out the data, the trajectory, the anomalies, the strange physics that make this object so difficult to explain. We'll walk through the natural models and examine why they don't quite close the case. In the second act, we'll dive headfirst into speculation. We'll explore hypotheses about navigation, about possible destinations, about the staggering implications of an artificial origin. And in the third act, we'll zoom out. We'll look at recent observations from Mars, from other spacecraft, and we'll discuss future missions that might one day intercept an object like this. We'll try to synthesize what 3I Atlas teaches us about the universe and our tiny, fragile place within it. So, settle in. This is going to be a journey, and I warn you, not all of it will be comfortable. We're going to challenge assumptions, entertain wild ideas, and confront the possibility that our solar system is neither special nor central to whatever agenda this visitor might have. Whether it's a frozen relic from the birth of another star, or a probe built by minds we cannot imagine, 3I Atlas carries with it a message, one we are only just beginning to decode. The universe is bigger and stranger than we pretend, and sometimes the silence is louder than any signal we could ever hope to receive. Before we go any deeper, I want to ask you something. Where are you watching this from? What time is it in your corner of the world right now? Let me know in the comments below. I'm always fascinated by the global community that comes together around these mysteries. And if you're as captivated by this enigma as I am, if you want to follow every development as this story continues to unfold, make sure you subscribe to this channel. This is just the beginning. Let's start with the most fundamental piece of the puzzle, the one that defines its entire story, its path. To understand where it's going, we need precision. We need data. And as it turns out, we got some crucial help from a most unexpected place. The red planet itself. Knowing where something is going sounds simple, but in the void of space, precision is everything. A miscalculation of a fraction of a degree, an error in velocity of just a few meters per second, can compound over millions of kilometers, turning a confident prediction into a useless guess. For 3I Atlas, getting the trajectory right wasn't just an academic exercise, it was the master key to unlocking the object's intentions. Was it tumbling blindly, a leaf on the cosmic wind? Or was its path a carefully plotted course, showing signs of a design that mere physics couldn't account for? The European Space Agency's silent sentinels at Mars, the ExoMars Trace Gas Orbiter and Mars Express, both circling the red planet, found themselves in the perfect position at a pivotal moment. As 3I Atlas made a relatively close pass by Mars, these robotic explorers turned their sophisticated instruments away from the rusty plains below and toward the dark of space. They imaged the comet, tracked its precise motion against the backdrop of fixed stars, and measured its fluctuating brightness. These observations, combined with the torrent of data from Earth-based telescopes and the keen eye of the Hubble Space Telescope, allowed astronomers to refine the object's orbit with an accuracy that was previously unimaginable. Why does this matter so profoundly? Because the more precisely you know an object's path, the more you can speak with authority about its past and its future. You can rewind the cosmic tape, extrapolating backward to figure out its origin, which distant star system might have ejected it, and how long it has been wandering in the interstellar darkness. You can fast forward, projecting its path to see where it's headed next, whether it will pass close to any other worlds, and whether its trajectory shows the subtle fingerprints of gravitational assists, or more provocatively, deliberate manoeuvres. For 3I Atlas, Legamain de 14 1825 1909, the refined orbit revealed a crucial, definitive truth. This object is on a hyperbolic trajectory. It is not bound to our Sun. It is not coming back. It is leaving the solar system permanently, accelerating outward into the true interstellar void, and nothing short of a catastrophic collision will ever stop it. Hubble watched it as it raced away, a lonely sentinel measuring how its brightness faded and how its ephemeral tail evolved. Those observations confirmed what the cold, hard math of orbital mechanics already screamed. 3I Atlas is an escape artist. Its velocity exceeds the Sun's escape velocity, meaning it is unbound, free, destined to wander the galaxy until another star's gravity captures it, or it drifts alone forever in the immense nothing between the stars. For astronomers who prefer their explanations clean and natural, this is perfectly consistent with an interstellar comet, a chunk of ice and rock flung out of another star system by a gravitational slingshot millions or billions of years ago. But for those who dare to entertain more exotic ideas, it raises profound and unsettling questions. If it is artificial, where is it going with such purpose? Did it complete its mission here, whatever that mission was? Or is our solar system merely one stop, one refueling point, one data collection node on a much longer, unimaginable journey? Added another layer of deep intrigue. By viewing the comet from a different angle, from a new vantage point millions of kilometers from Earth, the data from the Martian orbiters allowed scientists to constrain the object's rotation, infer its shape, and map its activity patterns. They could see which parts of the surface were most active, where the mysterious jets were erupting, and how those jets changed as the comet moved along its path. This kind of multi-planet observation is exceptionally rare. Usually we are stuck with a single viewpoint from Earth, trying to infer a three-dimensional reality from two-dimensional images. With Mars in the mix, the geometry improved dramatically. The models got better, the uncertainty shrank, and that newfound precision opened the door to a new, more focused kind of speculation. Once you know the trajectory well enough, you can start to hypothesize about waypoints. You can ask whether the path shows signs of gravitational slingshots, whether it passed unusually close to Jupiter or Saturn, whether it might have used the gravity wells of those giant planets to alter its course. For 3I Atlas, the trajectory does show some fascinating alignments. It passed relatively close to the Sun at its perihelion, gaining velocity in the process. That's expected for any comet or asteroid, a simple consequence of orbital mechanics. But the timing and the specific geometry raised eyebrows. Some researchers noted, with a sense of unease, that if you were designing a mission to extract the maximum possible energy from the Sun's gravity, you would aim for a trajectory almost exactly like this one. You would dive in close, fire your engines at perihelion, where your velocity is at its absolute peak, and use the O-berth effect, a trick of orbital mechanics, to amplify your thrust exponentially. That's rocket science 101 for any interplanetary mission we plan. For a comet, it's supposed to be just a coincidence. Or is it? Let me be perfectly clear. No one has proven that 3I Atlas performed a maneuver. No one has detected the telltale signature of rocket exhaust, or unusual electromagnetic emissions, or any other definitive sign of active propulsion. But the trajectory is hauntingly consistent with it, and when you combine that with the other anomalies, the non-gravitational acceleration, the strange composition, the bizarre polarization signature, you start to see why a growing number of scientists are willing to entertain the idea that this object isn't entirely passive. It might be responding to forces we haven't accounted for, forces that aren't just simple outgassing and sunlight pressure. It might be doing something. The implications of this ripple outward, disturbing the calm waters of our cosmic isolation. If the trajectory is deliberate, if it has been designed or subtly influenced by something other than blind physics, then the object's future path becomes a map. You can start to guess where it's headed. You can ask whether it's aiming for another star, whether it's plotting a course through the galactic plane, whether it's using the sun and planets as stepping stones the way ancient mariners used islands. This is the navigational hypothesis, and we will dive into it more deeply soon. For now, just hold on to this idea. Precision matters. The better we know the path, the more we can speculate about the purpose. And thanks to Mars, thanks to those orbiters that happen to be watching at just the right moment, we know the path of 3I Atlas better than we have ever known any interstellar visitor before. But knowing where it's going is only half the puzzle. The other half, the more deeply strange half, is understanding what it's made of, how it's behaving, and why it so stubbornly refuses to act like a normal comet. That's where the anomalies come in, and there are 8 of them that have left scientists utterly baffled. Let me walk you through the list, piece by piece. This is where the mystery stops being an academic curiosity and starts to feel genuinely unsettling. 3I Atlas doesn't just break one rule, it breaks 8 of them. At least, that's according to the compiled observations from telescopes around the world and in space. Each anomaly, taken alone, might be dismissed as a fluke, an observational error, or a rare but natural phenomenon. But when you stack them together, when you look at the cumulative weight of all these oddities, you start to realize that something fundamental about this object doesn't fit our models. It's like a jigsaw puzzle, where every single piece is slightly the wrong shape, and no matter how hard you try to force it, they simply will not snap into place. First, the ecliptic alignment. Think of the solar system as a vast, flat disk. This is the ecliptic plane, the highway where all the planets orbit. Most interstellar objects that wander into our neighbourhood arrive from random, chaotic angles, reflecting the three-dimensional nature of galactic space. But 3I Atlas did not. It came in along a path that was suspiciously, almost impeccably, close to the plane of the solar system. For an interstellar visitor, arriving along that plane is like a stranger walking into your house through the front door, instead of crashing randomly through the roof or a wall. It's not impossible, but it is statistically unusual. It suggests, quietly, that perhaps the object's trajectory was influenced by something other than a random, violent ejection from another star system. Or it could just be dumb luck. But it's the first red flag. Second, this is one of the most visually and physically strange behaviours. Normal comets have tails that stream away from the sun, pushed relentlessly by the solar wind and radiation pressure. 3I Atlas has that, but it also has something else, a jet of material streaming toward the sun. This is called an anti-tail, and it is a rare and poorly understood phenomenon. It happens when a comet releases material in a particular direction, usually from a localized active region on its surface, and that material gets illuminated and arranged in such a way that it appears to point sunward. It isn't defying physics, not exactly, but it is unusual. And for 3I Atlas, it was one more thing that didn't quite fit the standard, comfortable profile of a comet: the non-gravitational acceleration. This is the big one, the anomaly that sparked the most intense debate and the first whispers of what if. As 3I Atlas moved through its orbit, it sped up in ways that the sun's gravity alone could not account for. Now, comets do this all the time due to outgassing. When the ice on their surface heats up and sublimates directly into gas, the escaping material acts like a tiny, natural rocket engine, pushing the comet in the opposite direction. For most comets, this effect is well understood and beautifully predictable. For 3I Atlas, the acceleration was stronger than expected, and the models that tried to explain it using standard outgassing physics struggled and ultimately failed to match the observations perfectly. We'll come back to this in a moment, because new research has since offered a plausible natural explanation. But at the time of its discovery, it was utterly baffling. It was as if the comet had a gentle, silent throttle of its own. Fourth, the nickel emissions. This is the anomaly that Avi Loeb would later make the cornerstone of his argument. He claimed that 3I Atlas was emitting nickel vapour at a rate of about 4 grams per second, with a startlingly small amount of iron mixed in. This is unusual to the point of being bizarre. In most astronomical contexts, nickel and iron are cosmic siblings, formed together in the same stellar forges and bound up in similar minerals and alloys. For an object to be ejecting one without the other is strange. Loeb suggested that the nickel might be forming nickel tetracarbonyl, a volatile compound that is rare in nature but common in industrial chemistry on Earth for refining nickel. If that's true, it could hint at a surface that has been processed, engineered, or manufactured. Of course, other scientists pushed back immediately, arguing that the nickel detection might be an artifact of the spectroscopic models, or that there are natural processes we don't yet understand that could produce similar signatures. But the debate is far from settled. The nickel is still there in the data, a stubborn, metallic mystery. Fifth, the water fraction. This anomaly challenges our very definition of a comet. Most comets are dirty snowballs, made primarily of water ice, mixed with dust and other volatiles like carbon monoxide and carbon dioxide. 3I Atlas turned this idea on its head. It had very little water. Its emissions were dominated instead by carbon monoxide and carbon dioxide, with water taking a distant back seat. This isn't impossible. We know that some comets, especially those from the outer reaches of a solar system or from interstellar space, can have different compositions. But it is unusual enough to raise sharp questions. Why is this object so dry? Was it formed in a different kind of environment, perhaps around a star with a different temperature or chemical makeup? Or is something else, something more active, going on? The polarization anomaly. When light reflects off a surface, it can become polarized, meaning the light waves align in a particular direction. Astronomers measure this polarization to infer properties like grain size, surface roughness, and composition. It's a powerful diagnostic tool. For 3I Atlas, the polarization signature was unlike anything ever recorded. It plunged to a deeply negative value of -2.7%, far more extreme than any comet astronomers had ever modelled. This suggests that the dust grains or the surface structure of this object are unlike anything we've encountered in our own solar system. It could mean the object has been irradiated for eons by cosmic rays, altering its surface chemistry. It could mean the grains are unusually large or unusually small. Or it could mean something we haven't even thought of yet. The polarization is a window into the object's history, and for 3I Atlas, that window is showing us a picture we do not recognize. Seventh, the WOW signal connection. This one is highly speculative, bordering on the absurd, but it is too intriguing to ignore. 1977. A radio telescope in Ohio detected a powerful, narrow-band signal from space that lasted for 72 seconds and was never, ever repeated. It became known as the WOW signal, and it remains one of the most famous unsolved mysteries in the history of SETI. The report on 3I Atlas noted, almost in passing, that the object's trajectory, when extrapolated backward in time, passes through the same region of the sky where the WOW signal originated. Is this meaningful? Almost certainly not. The odds of a connection are astronomically small, and there is no known physical mechanism that would link a comet to a transient radio burst from decades ago. But the coincidence is eerie, and it adds another layer of potent mystique to the object's story. Eighth, the perihelion timing and the Oberth window. As mentioned earlier, 3I Atlas reached its closest approach to the Sun at a moment that, from an engineering perspective, would be ideal for executing a high-efficiency maneuver. The Oberth effect allows a spacecraft to gain a tremendous amount of velocity by firing its engines when it is moving at its fastest, right at perihelion. For 3I Atlas, the timing aligned perfectly with this window of opportunity. That doesn't prove anything, but it opens the door wide to speculation. If the object had engines, if it wanted to maximize its energy gain from the Sun's gravity, this is exactly when and where it would fire them. And if it did, we might never have noticed, because the acceleration could have been masked by the natural outgassing that was already occurring. So, there you have it. 8 anomalies. 8 things that make 3I Atlas stand out from the crowd of celestial objects like a single lit window in a dark skyscraper. None of them, by themselves, are smoking guns, but together they paint a compelling and deeply strange picture of an object that is either the most unusual natural comet ever discovered, or possibly something more. The question now becomes, can we explain all of this with natural physics? Or have we exhausted the possibilities of the mundane, forcing us to start considering alternatives that lie at the very edge of science? Before we leap to conclusions about interstellar probes and alien spacecraft, we owe it to ourselves, to the spirit of scientific rigour, to exhaust the boring explanations. Because here is the crucial thing we must always remember. Nature is weird. Profoundly, endlessly, creatively weird. The history of astronomy is littered with the ghosts of phenomena that looked utterly inexplicable, that seemed to scream, "Intelligence!" until someone sat down, did the math, and found a beautiful, natural explanation. Pulsars, with their perfectly timed radio beats, were once seriously considered as potential alien beacons. Fast radio bursts were profound mysteries. Even the acceleration of Oumuamua, the first interstellar visitor, sparked a firestorm of speculation about artificial propulsion until more sophisticated models showed that outgassing of hydrogen ice could account for its behaviour. So, when we look at 3i Atlas and its catalogue of wonders, we have to ask the hard, disciplined question: is there a natural process, no matter how complex, that can explain these anomalies? According to a wave of recent research, the answer is a tentative but firm maybe. In November of 2025, a physicist named Florian Neuart published a sophisticated thermophysical model that attempted to explain 3i Atlas's most glaring anomaly, the non-gravitational acceleration, using nothing more exotic than the outgassing of carbon monoxide and carbon dioxide. This wasn't a hand-waving argument, it was a detailed, brute force simulation, a Monte Carlo model that accounted for the comet's rotation, its surface temperature, the distribution of active regions, and the complex way gas escapes from localized jets. The core idea is elegant in its simplicity. If the comet isn't outgassing evenly in all directions like a perfect sphere, if it has jets or vents that preferentially emit gas from certain areas, then the net thrust can produce acceleration that looks anomalous and directed, but is actually just a simple consequence of asymmetry. This is called anisotropic outgassing, and it is a well-known, though complex, phenomenon in comet science. The question for 3i Atlas was whether this effect was powerful enough to explain the significant push we observed. Art's model said yes, it is possible, under very specific conditions. He assumed a nucleus with a radius between 0.5 kilometre and 3 kilometres, which fits with the observed brightness and activity levels. He then simulated outgassing from active regions covering less than 1% of the surface. These could be cracks, fissures, or vents where the ice was exposed and sublimating violently. The gas escapes, pushes the comet in the opposite direction, and the rotation of the nucleus causes the direction of that thrust to change over time. When you add it all up, integrating the forces over the entire orbit and accounting for the changing distance from the Sun, the model successfully reproduced the observed non-gravitational acceleration. The math worked. The model fit. The crucial caveat that keeps the mystery alive. The model explains one anomaly, the acceleration. It is a powerful and compelling explanation for that single piece of the puzzle. But it does not explain the nickel emissions. It does not explain the extreme, record-breaking polarization. It does not explain the curiously low water fraction, or the anti-tail jet, or the suspicious ecliptic alignment. It is a piece of the puzzle, an important one, but it is very far from being the whole picture. And Neuart himself was careful to note that his model rests on certain key assumptions. The active fraction has to be very small. The gas has to be dominated by carbon monoxide and carbon dioxide, not water. The rotation has to align in a particular way. If any of these assumptions are off, even slightly, the model begins to break down. So, while the natural explanation for the acceleration is plausible and elegant, it is not comfortably complete. There are still gaps, still unanswered questions that the physics, as we currently understand it, does not address. One of the most interesting findings from Newhart's work was that more exotic volatiles, things like methyl hydride or other organic compounds, actually underproduced the needed thrust. You specifically need carbon monoxide and carbon dioxide to get the acceleration right. This is reassuring in some ways, because it suggests the comet's composition, at least in terms of its dominant gases, is within the realm of the known. But it also raises another, parallel question. If the comet is mostly carbon monoxide and carbon dioxide, where did all the water go? Most comets are thought to form in regions where water ice is the primary building block. 3I Atlas seems to have formed somewhere else, somewhere colder or richer in carbon. This could mean it came from a fundamentally different kind of star system, one where the protoplanetary disk had a unique chemical mix. Or it could mean the object has been profoundly processed, its original water depleted or locked away, altered by radiation or heat during its multi-million-year journey through interstellar space. The natural explanation also has to contend with the issue of timing. The model assumes the outgassing is driven purely by solar heating, meaning the comet's activity should peak predictably near perihelion and then taper off as it moves away from the Sun. And while this general trend was observed, there were subtle hints, whispers in the data, that the acceleration didn't behave exactly as expected. Some of the jets seemed to persist a little longer than the models predicted. Some of the activity was detected at distances where the Sun's heat should have been too weak to drive significant sublimation. These are small discrepancies, minor nagging inconsistencies, but they are there. And they keep the door to alternative explanations open, if only just a crack. So, where does this leave us? The natural model for the acceleration is compelling. It shows convincingly that you do not need to invoke alien technology to explain the core anomaly that started this entire mystery. But it does not close the case, not even close. It doesn't account for all 8 anomalies, and it doesn't explain the most profound unease that 3I Atlas inspires. Why does this one object seem to break so many rules simultaneously? Maybe 3I Atlas is simply a statistical fluke, a weird comet, an outlier that happened to arrive on our doorstep with a unique combination of properties we've never seen before. Or maybe the natural explanation is only part of the story, a layer of truth hiding a deeper, more startling reality. Before we dive into those more speculative waters, there is one more piece of the physical puzzle we need to examine, one that takes us right down to the surface of the object itself. Because the way light reflects off 3I Atlas, its bizarre polarization signature, is telling us something profound about what this thing is made of and how it has been shaped by its epic journey. And that story is just as strange as everything else we've encountered so far. When you shine light on a comet, the light doesn't just bounce back in a simple, predictable way. It scatters, it reflects, it interacts in a complex dance with the countless dust and ice grains on the surface. And in that process, it becomes polarized. Polarization is a measure of how those reflected light waves become oriented, and it is a powerful, almost magical tool for astronomers. It allows them to infer properties they could never see directly. The smoothness or roughness of a surface, the size of the dust grains, even the basic composition of the material. Smooth surfaces polarize light differently than rough ones. Tiny, micron-sized grains scatter light differently than large, pebble-sized ones. Ice, rock, and complex organic compounds all leave their own distinct fingerprints in the polarization signature. For most, polarization follows a predictable, well-mapped pattern. There's a positive branch where the polarization increases with the viewing angle, and a negative branch, usually quite shallow, where the polarization dips slightly below zero at specific angles. It's a familiar pattern, a comfortable celestial rhythm. 3I Atlas shattered that rhythm. Its negative polarization branch didn't dip slightly, it plunged. It reached a staggering -2.7%, far deeper, far more extreme than any comet astronomers had ever measured or modelled before. This wasn't just unusual, it was an outlier of historic proportions. It suggests that the surface of this object, or at least the dust and grains being ejected from it, have physical properties that simply do not match anything in our standard catalogues of solar system materials. This raises an immediate and critical question. What could possibly produce such an anomalous polarization? The scientific detectives got to work, exploring several possibilities. One leading theory is grain size. If the dust grains are much larger or much smaller than typical comet dust, the scattering properties can change dramatically. Large grains, on the order of tens or even hundreds of microns across, tend to produce deeper negative polarization. Very small, sub-micron-sized grains can also produce unusual effects. But the models that tried to fit the 3i Atlas data using grain size alone struggled. They could get close, but they couldn't match the exact depth and shape of the polarization curve without invoking additional complicating factors. It wasn't a perfect fit. Another possibility is surface roughness. If the comet's nucleus, or the dust grains themselves, are unusually rough, porous or fluffy, the light can scatter in intricate ways that amplify the negative polarization. This kind of extreme roughness can develop over time as a result of relentless sublimation, where the ice evaporates and leaves behind a fragile, porous structure, like a cosmic sponge. Or it could be the result of radiation processing, where high-energy particles from space bombard the surface for eons, sandblasting it and altering its texture at a microscopic level. We will come back to radiation in a moment, because it is becoming a central part of this story. A third possibility, and this is where the science starts to border on speculation, is that the composition itself is exotic. Maybe the dust isn't just simple rock and water ice. Maybe it contains unusual minerals, complex organic compounds, or even manufactured materials that we haven't encountered before. Some researchers have suggested that the polarization could be explained if the surface contains a great deal of carbonaceous material, the dark, sooty stuff that's common in some primitive asteroids. But 3i Atlas doesn't look particularly dark. Its colour is a distinct reddish hue, which is more consistent with iron-rich minerals, or organic tholins, those complex tar-like molecules that form when simpler compounds are irradiated by ultraviolet light or cosmic rays. The polarization anomaly ties directly back to one of the other great mysteries, the object's fundamental structure. When you combine the polarization data with the spectroscopic observations, the emissions of carbon monoxide and carbon dioxide, the notable lack of water, you start to build a coherent, if disturbing, picture. You start to see an object whose outer layers have been profoundly and irrevocably altered. We are not seeing its pristine interior. We are not seeing the real 3i Atlas, not as it was born. We are seeing a crust, a weathered shell, a mask that has been shaped and forged by its unimaginably long journey through the harsh environment of interstellar space. And that brings us to a transformative concept, one that has gained tremendous traction in explaining this object: cosmic aging. The idea that objects wandering between the stars are being continuously processed, like stones in a cosmic river, by the relentless rain of galactic cosmic rays. Think of it like this. Imagine you left a brand new car outside, exposed to the elements for 1,000,000 years. The paint would be gone, the metal would be rusted, the glass would be frosted and pitted, the interior would be dust. The car would be utterly unrecognizable. Now scale that up to a cosmic level. 3i Atlas has been wandering through the galaxy for who knows how long, maybe tens of millions, perhaps hundreds of millions of years. For all that time, it has been exposed to a constant, invisible downpour of high-energy particles, protons and atomic nuclei accelerated to nearly the speed of light by supernovae and other violent events. These galactic cosmic rays slam into the surface, breaking chemical bonds, rearranging molecules, and slowly, inexorably, transforming the outer layers into something entirely new. This process is called GCR processing, and a landmark research paper published in October 2025, led by Dr. Roma Maggiolo, argued that it is the master key to understanding 3i Atlas. The evidence, they showed, comes from multiple independent sources, all pointing to the same conclusion. The extreme carbon dioxide to water ratio, a classic signature of cosmic ray processing, which can convert carbon monoxide into carbon dioxide. The elevated carbon monoxide levels, consistent with a processed crust. The red spectral slope, a known effect of radiation creating complex organic molecules. And yes, the extreme polarization signature, it fits perfectly with a surface that has been irradiated, altered, and crusted over by billions of years of exposure to the interstellar medium. The outgassing we observed, according to this model, wasn't coming from the object's original pristine ice. It was coming from a processed zone, a radiation-transformed rind estimated to be about 15 to 20 meters thick, where the cosmic rays have worked their alchemy, creating a shell that is chemically distinct from the interior. This has profound implications, with two possible paths forward, each as intriguing as the other. The first is that this is a purely natural process, common to all ancient interstellar objects. Every comet, every asteroid that's been wandering the galaxy for eons will develop a similar crust. In this case, 3I Atlas is just an old traveller, its appearance shaped by the same universal forces that shape everything in the void. It is a perfectly natural relic. The second possibility is more unsettling. What if the radiation processing isn't just an accident of time? What if it was part of the plan? What if something, some intelligence, deliberately used this natural process, either to shield sensitive systems buried deep beneath the crust, or to create a perfect camouflage, a disguise that makes an artificial probe look, for all intents and purposes, exactly like a natural comet? If 3I Atlas is artificial, then this weathered, cosmic ray-blasted exterior could be a feature, not a bug. It could be the ultimate stealth technology, developed not in a lab, but by using the galaxy itself as a tool. It could be hiding something. Be perfectly clear, there is no direct evidence for that. It is pure speculation, a thought experiment at the farthest edge of science. But it is the kind of speculation that makes you pause, that makes you look at the data with new eyes and wonder what you are really seeing. Because the surface of 3I Atlas, with its extreme polarization and its processed crust, is telling us one thing above all else. Appearances can be deeply, fundamentally deceiving. What we observe may not be the truth. It may just be the carefully aged shell of something older, stranger, and infinitely more complex than we can currently comprehend. And that realization, that we might be looking at a mask, brings us to the second act of this investigation. We have laid out the data, we've walked through the anomalies and explored the natural explanations. Now, it is time to ask the harder, more dangerous questions. If 3I Atlas isn't just a comet, if there is even the slimmest chance that it is something more, then what is it doing? Where is it going with such silent purpose? And what does its enigmatic journey tell us about the universe and our own small place within it? Let's entertain a thought experiment. What if 3I Atlas isn't just drifting mindlessly? What if it is, in some way, navigating? I know how that sounds. It sounds like the plot of a science fiction novel, the kind of wild idea that belongs on the fringe, not in a serious discussion about a real astronomical object. But stay with me, because the trajectory of this comet, the precise way it moved through our solar system, is at least consistent with the idea of deliberate course corrections. And if we are going to take its entire portfolio of anomalies seriously, if we are going to give the artificial hypothesis its fair due, then we have to ask, could it be using the sun and planets as navigational markers, the way ancient Polynesian sailors used the stars, the waves, and the flight of birds? It's called a gravitational slingshot, and it is not science fiction. It is the bedrock of modern interplanetary travel. When a spacecraft passes close to a planet, it can steal a tiny fraction of that planet's orbital momentum, gaining velocity and altering its trajectory without expending a single drop of fuel. This is how we sent the Voyager probes to the outer planets, how we guided Cassini to Saturn, how New Horizons reached Pluto. The trick is all in the geometry, approaching the planet at the exact right angle and speed so that the gravitational interaction bends your path in precisely the direction you want to go. Master this, and you can chain multiple slingshots together, hopping from world to world, building up speed until you are flung toward your ultimate destination. Now, 3i Atlas didn't make any dramatically close passes to Jupiter or Saturn on this particular trip through our system. But its trajectory was far from random. It came in along the ecliptic plane, the precise highway where the planets reside. It reached its perihelion at a time that was, from an engineering perspective, ideal for executing an Oberth maneuver. And it is now exiting the solar system on a path that will carry it past the outer planets, Neptune and beyond, before it finally escapes into the galactic void. If you were designing a probe to conduct a broad survey of a star system, to sample the gravitational and magnetic fields of multiple planets, to map the boundaries of the heliosphere, this is roughly the kind of path you might choose. It's efficient, it's comprehensive, and it requires a minimal expenditure of energy. Let me be clear, I am not saying that is definitively what is happening. I am saying the observed path is consistent with that scenario. And in the absence of definitive proof, consistency is the fertile ground where speculation grows. So, let's speculate. What would it take for an object like 3i Atlas to navigate deliberately? First, it would need a means of propulsion. Not necessarily powerful, roaring engines, but just enough capability to make small, precise course corrections, to tweak its velocity at key moments. The non-gravitational acceleration we observed could be evidence of that, although as we've seen, it can also be explained by asymmetric outgassing. Second, it would need a navigation system. It would need to know where it is going, and how to adjust its path to get there. This implies sensors, star trackers, perhaps even a sophisticated guidance computer. Third, it would need to be phenomenally robust. It would need to survive the unimaginable harshness of interstellar space, the relentless cosmic radiation, the near absolute zero cold, the occasional micrometeoroid impact. And if it has been wandering for millions of years, it would need to be built to last, an artifact of almost godlike engineering durability. The Sun's magnetosphere adds another fascinating layer to this. This vast, invisible bubble of magnetic field, shaped by the solar wind, extends billions of kilometers into space. For a spacecraft with the right kind of sensors, the magnetosphere could serve as a brilliant navigational landmark, a way to orient itself relative to the Sun and the planets. Some researchers have speculated that truly advanced probes might use magnetic fields, not just gravity, as a primary navigational aid. If 3i Atlas was doing this, we would have no way of knowing, as we haven't detected any unusual magnetic emissions from it. But the possibility remains, a silent, untestable hypothesis. Window at perihelion is particularly tantalizing. At that moment, 3i Atlas was moving at its maximum velocity, and the Sun's gravity was pulling at its hardest. This is the absolute perfect time for a spacecraft to fire its engines, as the Oberth effect means that a tiny amount of thrust here produces a massive change in overall orbital energy. Even a small, brief burn could have altered its final trajectory by a significant degree. Did 3i Atlas do this? We have no proof. The acceleration could be entirely natural, but the timing is, once again, strikingly consistent with a planned maneuver. And if it did execute such a maneuver, it might have done something else at the same time. It could have released smaller, subprobes or instrument packages, objects far too small and dark for our telescopes to ever detect, seeding our solar system with silent, watching eyes. Brings us to the grandest version of this idea, the waypoint hypothesis. If 3i Atlas is artificial, then our solar system might not be its destination. It might just be a pit stop, one refueling depot or data collection node among millions scattered across the Milky Way. Imagine a vast, ancient network of such probes, each one programmed to visit star systems, gather specific data, and then move on. They wouldn't need to report back in real time. The distances are too vast, the delays too great. They would simply wander, collecting information, storing it in vast memory banks, and perhaps transmitting it in compressed bursts when they periodically pass close to another probe or a fixed relay station. In this scenario, Our solar system is just another entry in a cosmic catalogue. We are not special. We are not the target. We are just one more stop on an endless, automated journey. This idea is simultaneously humbling and terrifying. Humbling because it suggests we are not the centre of anyone's attention, that the universe is carrying on its business with a profound indifference to our existence. Terrifying because it implies that we are surrounded, that the galaxy is buzzing with intelligence and technology and intentions we cannot fathom. If probes like 3i Atlas are common, if they are crisscrossing the galaxy by the thousands or millions, then we are living in a cosmos that is far more active and populated than we ever dreamed. And yet, we are utterly alone, isolated by the very distances and timescales that allow this network to exist, unable to communicate with whatever minds sent these silent travellers on their way. The navigational hypothesis also forces us to confront the question of energy. If 3i Atlas is propelled, if it is making deliberate course corrections, where does the power come from? Solar panels are useless in the outer solar system and beyond, where sunlight is a faint memory. Nuclear power is a possibility. Radioisotope thermoelectric generators, like those on Voyager and Curiosity, could function for decades, even a century. But 3i Atlas might be millions of years old. It would need something far more advanced, perhaps a power source based on principles we don't yet understand, or a design of such sublime efficiency that it barely needs power at all, coasting on gravity and momentum for eons, with only the most occasional, minuscule thruster burn. Or perhaps it needs no active propulsion at all. Maybe it is a masterpiece of passive design, an object engineered so brilliantly that it can navigate using nothing but natural forces. Think of a sailboat tacking against the wind, using the subtle interplay of forces to move in directions that seem impossible. A sufficiently advanced civilization might design probes that harness the gravity of stars, the pressure of starlight, the drag of the thin interstellar medium to steer themselves across the galaxy. In this case, 3i Atlas wouldn't need fuel. It would need only time and patience, drifting from system to system over millions of years, nudged by gravity into trajectories that serve some inscrutable, grand purpose. The sailor metaphor is apt. The ancient Polynesians crossed the vast Pacific without maps or compasses, using an intimate knowledge of the natural world, the stars, the swells, the clouds, the birds. They worked with the environment, not against it. If there are intelligences out there building interstellar probes, they might approach navigation in the same minimalist, elegant way, not with brute force rocketry, but by weaving their intentions into the very fabric of space-time, using what is already there. And if that is true, then 3i Atlas could be a masterpiece of this philosophy. A probe that looks like a comet because that is the most efficient way to travel, blending in perfectly with the natural debris of the galaxy, while quietly, patiently pursuing its mission. But here is the unsettling conclusion. If it is navigating, if it is using the sun and planets as waypoints, then it is succeeding brilliantly. It came in, it passed through, and now it is leaving. Whatever it came here to do, to observe, to record, to refuel, to deploy, it is done. We are watching it disappear into the outer darkness, a silent ship receding over the horizon, and we will never know what it learned, what it recorded, or where it is going next. That profound sense of a missed opportunity, of a first contact scenario slipping through our fingers before we even knew it was happening, is what drives a small but passionate group of scientists to propose ambitious intercept missions, fast, agile spacecraft that could chase down objects like 3i Atlas and examine them up close. Yet, the technology, the funding, the political will, it doesn't exist. By the time we could possibly mount such a mission, 3i Atlas will be a faint, unreachable speck, lost in the interstellar gloom. So, we are left with only questions. Is it navigating? Is our solar system a waypoint? Are we being catalogued, studied, or simply ignored? The data doesn't give us answers, only hints and haunting possibilities. But those hints are powerful enough to keep us watching and wondering. And that sense of wonder pushes us inevitably toward the next great question. Because if 3i Atlas is going somewhere, if its path is deliberate, then where is it bound? What destination, what goal could possibly justify a journey of such epic scale? Let's map out the possibilities, because once you accept that 3i Atlas is irrevocably leaving, that it is on an escape trajectory carrying it into the interstellar void, the next question becomes unavoidable, echoing in the silence it leaves behind. Where is it going? The answers range from the prosaic to the mind-bending, each one painting a different picture of the galaxy and our place within it. The first and most straightforward possibility is that it is heading for another star. Its velocity, a blistering 40 kilometers per second relative to our Sun, is impressive by human standards, but achingly slow on the cosmic scale. At that speed, it would take tens of thousands of years to reach even our very nearest stellar neighbours. Proxima Centauri, the closest star to our Sun, is about 4.2 light-years away. For 3i Atlas, that would be a 30,000-year journey, and that's assuming it's even headed in that direction, which, based on its current trajectory, it is not. It is heading out into the general direction of the constellation Lynx, toward a region of sky that is, from our perspective, largely empty, devoid of any notable close stars. But space is three-dimensional, and trajectories can be adjusted. Perhaps it is planning a mid-course correction centuries or millennia from now, a tiny burn that will redirect it toward a target we cannot see from here, a dim brown dwarf, a rogue planet drifting between the stars, or a stellar system still hidden in the galactic dust. Is that its destination is not another star, but the outer reaches of our own solar system. Not as a final goal, but as a survey zone. Beyond the orbit of Neptune, about 30 times farther from the Sun than Earth, lies the Kuiper Belt, a vast ring of icy bodies. Beyond that is the scattered disk, and farther still, the hypothetical Oort cloud, a spherical shell of comets that may extend halfway to the next star. If 3i Atlas is a probe, perhaps its mission parameters include a detailed survey of these remote, pristine regions, to study the gravitational influence of the unseen outer planets, to map the distribution of primordial material, to sample the boundary where the Sun's influence fades and the true galaxy begins. This would make perfect sense if the probe's builders were interested in a comprehensive understanding of stellar systems, not just a quick flyby of the inner planetary zone. The third possibility, and this one is the most difficult to grasp, is that it has no destination at all. Perhaps 3i Atlas is a drifter, a von Neumann probe programmed to wander the galaxy indefinitely, collecting data wherever it goes, with no fixed endpoint or final home. In this profoundly lonely scenario, the probe doesn't even need to report back. It just records, stores its findings in a vast memory, and continues on its way. Maybe it is part of a distributed galactic intelligence, a network where individual probes act as nodes, gathering information and occasionally exchanging it in fleeting high-speed bursts when their paths randomly cross in the deep. Or maybe it is a relic, the last remaining artifact of a civilization that died out millions of years ago, still carrying out its programmed instructions long after its creators have turned to dust. That is a haunting thought. A machine drifting through the cosmos with no one to receive its messages, no one to care about the eons of data it has collected. But it is a plausible model. If you are designing a probe to last for millions of years, a drifter makes sense. You don't need to maintain a fragile communication link over interstellar distances. You just let the probe go, confident that it will outlive you, outlive your species, outlive your very star. Let's dig into the mechanics of these scenarios for a moment. If 3i Atlas is artificial, what kind of mission profile would it have? One model is the Scout. A Scout probe would be small, fast, and minimally equipped. Its job is simple: visit star systems, make basic observations, number of planets, atmospheric compositions, signs of technology or biology, and move on quickly. It wouldn't linger. It wouldn't deploy instruments. It would be a triage unit, gathering just enough data to determine whether a system is interesting enough to warrant a more detailed follow-up mission from someone or something else. 3i Atlas fits this profile well. It passed through our solar system relatively quickly, spent most of its time in the planet-rich inner regions, and is now departing. If it's a scout, maybe it has already transmitted its brief, concise report. 1 G-type star, 8 planets. Third planet shows signs of technological civilization. Primitive. No immediate threat or strategic value. Continuing on. Another model is the Surveyor. A Surveyor probe would be more sophisticated, carrying a suite of instruments to measure gravitational fields, magnetic environments, solar wind composition, planetary atmospheres, and more. Its mission would be to build a detailed, three-dimensional map of the star system, not just a quick snapshot. This kind of probe might linger longer, might use gravitational assists to alter its path for better views, and might even deploy smaller sub-probes or disposable sensors. 3i Atlas didn't obviously do this, but perhaps its own instruments were sufficiently advanced to gather all the data it needed from a distance. Or perhaps we simply failed to detect the tiny, stealthy instruments it released. A third model is the Archive. An archive probe wouldn't primarily gather data about star systems. It would carry data within itself. This is the concept of a Bracewell probe, named after the physicist who proposed it. The probe would enter a star system and wait, listening for signs of intelligence. Once it detected a technological species, it would attempt to make contact, delivering a message or an entire library of information from its builders. 3i Atlas has not made contact. It has not signaled us. It has done nothing to announce its presence. But maybe it's waiting, listening to our radio and television broadcasts, assessing our level of development. Or maybe we've already missed our chance. Maybe it came, it listened, and it judged that we were not yet ready for whatever knowledge it carries. Now it is leaving, its secrets intact, moving on to a species that is wiser or quieter or simply more interesting. Thank the energy if iAtlas has been travelling for millions of years. It needs a power source that can last that long. Our best technology, radioisotope thermoelectric generators, RTGs, use plutonium-238, which has a half-life of about 87 years. After a few centuries, an RTG would be too weak to power anything. So, if 3i Atlas is ancient, it needs something else entirely. Perhaps a different isotope with a much longer half-life, or a nuclear fission reactor, or a technology we can't conceive of, harnessing zero-point energy or dark matter. Or maybe it doesn't need continuous power. Maybe it spends 99.9% of its journey in a state of deep dormancy, a cosmic hibernation, only waking up when it enters a new star system, using stored power or harvesting solar energy to run its systems for a few months or years before shutting down again for the long, dark cruise. Interstellar pit stop idea is particularly fascinating. Imagine a galaxy crisscrossed with highways, where star systems are like gas stations and rest stops. Probes travel from star to star, using gravitational assists to maintain momentum, occasionally stopping to refuel, perhaps by harvesting cometary ices for reaction mass, or to transmit stored data to a hidden, automated relay station in the Oort cloud. In this model, our solar system is just one stop among billions. We're not special. We're not the end goal. We're just here. Another yellow star with a handful of planets, worth a quick visit to top up the tanks and check the maps, but nothing more. That perspective is both humbling and profoundly isolating. It suggests a galaxy teeming with activity, with intelligence, with purpose, but that we are peripheral to it all, irrelevant. We're not being studied intently. We're not being prepared for contact. We're just being noted, catalogued, and filed away in some vast galactic database. And then, of course, there is the possibility that we are wrong about all of this. Maybe 3i Atlas isn't going anywhere because it has no purpose. Maybe it is just a comet, a beautifully, fantastically unusual one, but a comet nonetheless. a chunk of ice and rock flung out of another star system by a random gravitational kick, following the serene and mindless laws of physics with no intelligence, no mission, no design. Maybe its trajectory is a series of coincidences. Maybe its anomalies are merely artifacts of our own incomplete models, quirks of chemistry and radiation that we will fully understand once we've studied a few dozen more interstellar objects. Maybe we are, as humans have always done, seeing patterns in the randomness, imposing meaning on the meaningless because we are natural-born storytellers in a universe that may have no story to tell. But even if that is the ultimate boring truth, the questions 3i Atlas has raised are real, and they are vital. Because someday, maybe not with this object, maybe not in our lifetimes, we will encounter an object that isn't natural. We will detect a signal, a structure, a trajectory that cannot be explained by physics and chemistry alone. And when that day comes, we need to be ready. We need to have the frameworks for thinking about it, the protocols for responding, and, most importantly, the humility to accept that we are not the only sentient minds in the cosmos. 3i Atlas, whether it is natural or artificial, is our training ground. It is a thought experiment made flesh, or rather, made rock and ice. It is teaching us how to think about the unthinkable, how to balance skepticism with wonder, how to investigate without jumping to conclusions. So where is it going? We don't know. Maybe toward another star. Maybe toward nowhere. Maybe on a journey that will outlast our species, our planet, and our sun. But the uncertainty, the not knowing, is an essential part of the mystery. And the mystery is the engine that keeps us watching, keeps us building better telescopes and faster spacecraft, because we are driven by the hope that someday we might catch up. Someday we might know. Until then, we are left with our speculation, and with one question that haunts every astronomer who has tracked this silent object across the sky. If it isn't here for us, then who is it here for? Before we can even begin to answer that, we need to hear from the scientist who has made this question impossible for the world to ignore. Loeb is not a fringe figure. He is a tenured professor at Harvard University, the former chair of its prestigious astronomy department, a prolific researcher with hundreds of peer-reviewed papers to his name. He is also, undeniably, one of the most controversial voices in modern astrophysics. Not because his science is bad, but because he is willing to say aloud the things that other scientists will only whisper. He is willing to entertain, with rigorous academic backing, the idea that some of the things we see in the sky might not be natural, that they might be technology built by intelligences that are not us. And when 3i Atlas appeared, Loeb did what he had done before with Oumuamua. He looked coldly at the data, identified the most stubborn anomalies, and suggested publicly, forcefully, that we must consider the possibility that this object is a probe. His argument finds its sharpest point with the nickel emissions. According to Loeb's analysis, 3i Atlas was ejecting roughly 4 grams of nickel vapor per second during its peak activity, with a curiously small amount of iron mixed in. This separation is the key. In the cosmic forge, nickel and iron are born together, fused in the hearts of massive stars, and often found alloyed together in the minerals of asteroids and comets. For an object to be spewing one without the other is peculiar. Loeb suggests that the nickel might be in the form of nickel tetracarbonyl, a compound with the formula NiCO4. It's a gas at relatively low temperatures, and on Earth, it is used almost exclusively in industrial processes for refining and purifying nickel. You do not find it in comets, you do not find it in asteroids, you find it in chemistry labs and metallurgical plants. If nickel tetracarbonyl is present in the coma of 3i Atlas, Loeb argues, it could be a powerful hint of a surface that has been processed, refined, or engineered. Perhaps the probe's builders used nickel-based alloys in its structure, and the gentle heating from the sun is causing this material to ablate away, carrying nickel atoms off as a gas. Or perhaps the nickel is a deliberate byproduct, an exhaust fume from some internal process we cannot comprehend. Either way, the composition is too specific, too refined, too much like the signature of a machine rather than a random chunk of cosmic debris. The scientific community predictably pushed back hard. Critics argue that the nickel detection itself might be an artifact of the spectroscopic models, that the signal could be contaminated by noise or misinterpreted. They point out, correctly, that we have only studied a handful of interstellar objects. Our understanding of their chemistry is in its infancy. Perhaps 3I Atlas is just unusual, not artificial. Maybe its parent star system had a unique chemical composition, richer in nickel and poorer in iron. Maybe there are entirely natural processes, weathering, irradiation, selective sublimation, that can concentrate nickel and produce emissions that look refined to our eyes, but are, in fact, completely natural. The debate is ongoing, fierce, and far from settled. But here is the crucial thing about Loeb's argument. He is not claiming to have definitive proof. He is claiming that the artificial hypothesis deserves serious consideration. And in science, that is a very different standard. You do not need proof to propose a hypothesis. You need anomalies, unanswered questions, gaps in the existing models that the new hypothesis can fill. And 3I Atlas has those gaps in abundance. The nickel is just one piece. There is also the non-gravitational acceleration, the ecliptic alignment, the extreme polarization, the trajectory that seems so purposefully arranged. Loeb is saying, look at the cumulative weight of all these anomalies. Look at how many things don't fit the standard model. At what point does the weight of the evidence become so heavy that we stop calling it a weird comet and start honestly asking if it might be something else? The problem is that something else is a loaded phrase. It implies intelligence, it implies technology, and in the current conservative climate of science, those implications are professional risks. If you suggest an object might be artificial and you are later proven wrong, you face ridicule. You lose credibility. You get labelled a sensationalist, a crank, someone who prioritizes headlines over rigor. Loeb has faced all of this, especially after his high-profile claims about Oumuamua. And yet, he persists. Not because he is certain, but because he believes the question is too important not to ask. He believes that science should be open to all possibilities, not just the safe, conventional ones. That progress often lies just beyond the boundaries of what we currently find comfortable. This Rigaud, let's take his argument seriously for a moment. Let's imagine that 3I Atlas is artificial. What does that actually mean? For Bit, it means we are not alone. It means there are, or were, other technological civilizations in the galaxy capable of building probes that can survive interstellar journeys. This in itself is not a radical claim. The Drake equation, the Fermi paradox, the entire field of SETI, all are built on the assumption that such civilizations could exist. The haunting question has always been, where are they? If 3I Atlas is a probe, it is an answer, and a deeply unsettling one. They are here, but they are silent. They are not trying to talk to us, they are just passing through, doing whatever their mission requires, utterly indifferent to our presence. Psychologist. Second, it means the probe is likely ancient. The evidence of heavy cosmic ray processing suggests it has been travelling through interstellar space for millions, perhaps tens of millions of years. If it was launched by a civilization, that civilization might be long gone. The probe could be a relic, an orphan, still dutifully carrying out its programming long after its creators have vanished into the dust of cosmic history. That is a sobering thought. It suggests that intelligence and the technology it creates might be fragile, that civilizations rise and fall, and the galaxy could be littered with the abandoned, silent tools of species that did not survive. Blockers. Third, it raises profound questions about intent. If the probe is here, what is it actually doing? Is it collecting data? Is it transmitting it somewhere? Is it interacting with anything, or is it just observing, a silent witness? We have detected no signals from 3I Atlas, no radio transmissions, no laser pulses, nothing that would indicate an attempt to communicate. But maybe we're not listening in the right way, on the right frequencies or at the right time. Or maybe it's not here to communicate with us at all. Maybe it's here to watch, to record, and to move on. That would explain its silence, its indifference, its unwavering trajectory out of our system. Congressional. 63. The counter-arguments, of course, are strong and voiced by the majority of the scientific community. Most scientists, even those who respect Loeb's intellect and courage, believe he is overreaching. They point to the natural explanations, the thermophysical models like Newitt's, the outgassing simulations. They argue, with considerable justification, that invoking alien technology is the last resort, that we must exhaust every conceivable natural possibility before we make that extraordinary leap. And they are right to be cautious. This is how science works, by systematically eliminating alternatives, by testing hypotheses and ruling out the ones that don't fit. The problem with 3I Atlas is that it doesn't fit any hypothesis comfortably. The natural models explain some anomalies, but not all of them, and not without forcing the data. The artificial hypothesis explains more of the anomalies in a cohesive way, but it requires us to accept a premise that is, at present, unverifiable and philosophically jarring. It is a choice between an incomplete natural explanation and a speculative, paradigm-shattering artificial one. Different scientists, based on their own tolerance for uncertainty and their philosophical priors, will make different choices. Loeb's role in this drama is therefore pivotal. He is not just another researcher presenting data, he is a provocateur, challenging the very norms of his field, pushing the boundaries of what is considered acceptable discourse, and forcing the entire community to confront uncomfortable questions head-on. He is saying, we have a powerful, ingrained bias toward natural explanations, and that bias might be blinding us to what is right in front of our telescopes. We repeat the mantra that extraordinary claims require extraordinary evidence. But what if the extraordinary evidence is already here, and we are simply refusing to see it because the claim is too extraordinary? It is a provocative, even dangerous position to take. It has made him a controversial figure, but it has also made him an immensely influential one. Because whether or not 3I Atlas is ever proven to be artificial, Avi Loeb has irrevocably changed the conversation. He has made it acceptable, or at least possible, to ask the question in serious scientific circles. And that matters. Because the next interstellar object might not be ambiguous. It might be obvious. And when that day comes, we will be grateful that someone had the courage to do the groundwork, to do the thinking, to practice asking the unthinkable. So, is 3I Atlas a probe? We do not know. But the fact that the question is on the table, debated by a Harvard professor and his peers in major journals, is a testament in itself to how deeply strange this object truly is. And the strangeness does not end with the nickel or the trajectory, because there is one final, masterful layer to this mystery, one that ties all the physical evidence together into a coherent and terrifying whole. The surface is not what it seems, and the reason why reveals something profound about the nature of reality itself, and the possibility that what we are observing is nothing more than an ancient, perfect mask. 2025, a team of researchers led by Dr. Roma Maggiolo published a paper that fundamentally shifted the paradigm for understanding 3I Atlas. They weren't trying to prove it was artificial. Their goal was far more straightforward: to understand its bizarre composition, the strange ratios of gases it was emitting, the very nature of its being. And what they discovered was that the object's outer layers have been profoundly and irrevocably altered by a force that permeates the galaxy: galactic cosmic rays. These are not mere rays of light. They are a brutal rain of high-energy particles, protons, atomic nuclei, electrons, all accelerated to nearly the speed of light by supernova shocks and other violent events. When these particles hit a solid surface in the vacuum of space, they don't just bounce off, they penetrate, smashing into atoms breaking chemical bonds, knocking molecules out of place, and triggering a cascade of nuclear and chemical reactions that would never occur otherwise. Over time, over millions of years, this relentless radiation processing transforms a surface utterly. Simple ices become complex organic goo. Carbon monoxide is converted into carbon dioxide. The surface darkens, roughens, and develops a thick, crusty rind of altered material that is chemically and physically distinct from the pristine interior. This isn't just theory. It has been demonstrated in laboratory experiments on Earth. Researchers take samples of comet-like ice, bombard them with high-energy particles in vacuum chambers, and watch as the material morphs. It darkens. Complex organic compounds form. The surface becomes pitted, porous, and crusted over. If you continue the bombardment, simulating millions of years of exposure, the crust grows thicker, eventually reaching depths of meters, even tens of meters. Therapists, the Maggiolo team argued, is exactly what has happened to 3I Atlas during its long exile in the interstellar desert. The object's most baffling properties, they showed, are not anomalies at all, but the predictable consequences of cosmic aging. The extreme carbon dioxide to water ratio, a classic signature of cosmic ray processing, which efficiently converts carbon monoxide into CO2. The elevated levels of carbon monoxide, consistent with a processed crust where these chemical transformations are ongoing. The red spectral slope, a known effect of radiation creating complex carbon-rich polymers known as tholins. And yes, the record-breaking polarization signature. It fits perfectly with a surface that has been irradiated, sandblasted, and altered into a state of extreme roughness and porosity over billions of years. According to their modelling, the outgassing we observed from 3I Atlas wasn't coming from the object's original virgin interior. It was emanating from a processed zone, a radiation-transformed shell estimated to be about 15 to 20 meters thick, where cosmic rays have worked their alchemy. The real 3I Atlas, its true composition and structure, could be completely different, hidden safely beneath this ancient, weathered crust. We were not studying the object itself. We were studying its disguise. This discovery has two profound implications, leading down two very different paths. The first path is purely naturalistic and entirely plausible. It means that 3I Atlas is simply very, very old. You do not develop a 20-meter thick processed crust in a few million years. You need tens of millions, perhaps hundreds of millions of years of exposure. This object has been wandering the galaxy for an epic duration, a silent survivor from an earlier epoch of the Milky Way's history. Its origin story becomes even more mysterious. What long-dead star system did it come from? Is that star still shining? Or has it itself gone supernova, scattering its children to the void? We will likely never know. In this view, 3I Atlas is a perfectly natural interstellar comet, its strangeness merely a badge of its incredible age and the harsh environment it has endured. However, is where the speculation becomes profound. What if this cosmic aging isn't just an accident? What if it is part of the design? What if an intelligence, understanding the laws of physics and the nature of the galaxy, deliberately uses this natural process as the ultimate camouflage? If you wanted to hide a probe, to make it look exactly like a natural comet, one of the most effective ways would be to simply let the galaxy do the work for you. You build your probe, you send it on its way, and you wait. After a few million years of exposure to galactic cosmic rays, it will have developed a thick, convincing crust. It will outgas like a comet. It will reflect light like a comet. It will have the colour, the composition, the polarization of a comet. It will be, for all intents and purposes, indistinguishable from a natural object. But beneath that shell, protected from the radiation and the prying eyes of species like us, could lie the probe's true structure, its engines, its computers, its sensors, its payload. Let me be perfectly clear. There is no direct evidence that this is the case for 3I Atlas. It is a speculation, a thought experiment that lives in the space between the data points. but it is a possibility that is chillingly consistent with the data. The natural explanation, that it's just an old, processed comet, is the simplest and most likely. But the artificial explanation, that something used cosmic ray processing as a perfect billion-year-long stealth technology, is also consistent with everything we have observed. We currently have no way to distinguish between the two based on remote observations alone. And that fundamental ambiguity, that inability to rule out the artificial hypothesis, even with this powerful new understanding, is what keeps the mystery of 3I Atlas vibrantly, frustratingly alive. The research also highlights, with painful clarity, how little we truly know about the population of interstellar objects. 3I Atlas is only the third one we've confirmed, after Oumuamua and 2I Borisov. Our sample size is minuscule. We don't have a baseline for what's normal. Perhaps every interstellar object that has been travelling for more than a few million years looks exactly like this: dry, carbon-rich, deeply polarised, and heavily processed. Or perhaps 3I Atlas is unique, a true outlier even among its wandering kin. We need more data. We need to find and study dozens, hundreds of these visitors before we can say what is strange and what is standard. The idea that the surface is a mask, that the true object is hidden beneath layers of radiation-altered material, connects to a deeper, almost philosophical question about the nature of observation itself. What are we really seeing when we point our telescopes at the heavens? We operate under the assumption that our instruments show us reality, that the light, the spectra, the images are faithful representations of what is out there. But they are not. They are interpretations. They are filtered through our atmosphere, our telescope optics, our detectors, and most importantly, our models and our preconceptions. We see only the surfaces, the exteriors, the parts of objects that interact with light and radiation. We never see the interiors. We never see the whole truth. We infer, we model, we guess. And sometimes, as with 3I Atlas, our guesses lead us to the precipice of uncomfortable, paradigm-shattering possibilities. So, here is where we stand. The cosmic ray processing model explains a great deal. It elegantly accounts for the composition, the gas ratios, the red colour, and the extreme polarization. It tells us that 3I Atlas is ancient, a veteran of the galactic dark, and that what we are seeing is a weathered, cosmic ray blasted shell. But it does not close the case. It does not tell us whether the object beneath the shell is a simple ball of ice or a complex machine. It does not tell us where it is going or what it is doing. It just adds another, deeper layer to the mystery, another powerful reason to wonder whether, in the cosmic game of hide and seek, we are even capable of seeing the hider. And that brings us, inevitably, to the biggest and most haunting question of all, the one that has been lurking beneath every observation, every anomaly, every hypothesis from the very beginning. If 3I Atlas isn't here for us, if it's not trying to contact us or study us or interact with us in any way, then what or who is it looking for? And what does its profound, unbroken silence tell us about our own place in the cosmos? Let's step back from the data, from the models, from the fierce scientific debates. Let's ask the question that truly matters, the one that 3I Atlas forces upon us not as scientists, but as conscious beings on a small world. If this object is a probe, if it has been sent by some intelligence to explore, to gather information, to execute a mission, then what is that mission? And more unsettlingly, why does its mission appear to involve ignoring us completely? The probe hypothesis isn't a single idea, it's a spectrum of possibilities, and each one paints a different and often uncomfortable picture of our cosmic significance. The first is the scout probe model. In this scenario, 3I Atlas is an advanced reconnaissance unit, a vanguard sent ahead of something larger. Its job is simple and efficient. Survey star systems, identify interesting features, planets with atmospheres, chemical biosignatures, technosignatures like radio emissions, and report back. If it finds something promising, perhaps a larger, more capable mission follows. A detailed survey, a science outpost, or even first contact. But if it finds nothing of interest, or if it finds a civilization it deems too primitive or too dangerous, it simply moves on. No follow-up, no second glance. The system is catalogued and filed away. Under this model, we may have already been evaluated and found wanting. Perhaps 3i Atlas scanned Earth, detected our sprawling cities, our atmospheric pollution, our chaotic radio and TV broadcasts, and concluded, technologically nascent, biologically aggressive, not yet ready for interaction. Or perhaps we're just boring. Maybe the probe's builders have encountered 1,000 civilizations like ours, all at a similar, fragile technological stage, all facing the same existential risks. We are not unique. We are not special. We are just another data point, noted and dismissed. The second model is the mothership scenario. In this version, 3i Atlas isn't the primary probe itself. It's a carrier vessel, a larger craft that transports and deploys smaller, specialized instruments. The mothership doesn't linger or conduct detailed surveys. It enters a system, follows an efficient trajectory, and at the optimal moment, perhaps near perihelion, it releases a cloud of tiny subprobes, each no larger than a grain of sand, equipped with tiny sensors and communicators. These microprobes then disperse, drifting through the solar system, monitoring planetary environments, listening to communications, gathering data over centuries. If this is true, we almost certainly missed the deployment. We were looking for one large anomalous object, not a swarm of microscopic ones. Those instruments could be among us right now, invisible, drifting in the high atmosphere or in orbit around the sun, silently watching, recording, and transmitting their findings back to the receding mothership. It is the archive, or relic. This is the loneliest version of the story. The probe was launched millions or even billions of years ago by a civilization that has long since vanished, extinct through war, disaster, or evolution into some post-biological form. The probe, however, remains. It is still carrying out its original programming, still gathering data, still following its trajectory, but there is no one left to receive its messages. Its builders are gone. Its home world is dust. It is an orphan, a ghost ship wandering the galaxy. It doesn't make contact because it can't. Its communication protocols are obsolete, its intended receivers long dead. All it can do is continue executing commands that lost their meaning eons ago. A monument to a forgotten empire. Each of these models forces us to confront a different, uncomfortable truth. If we're being evaluated, it means we are not the evaluators. We are the subjects, the specimens, being judged by criteria we don't understand, by a judge we cannot see. If we're being used as a deployment zone for microsensors, it means we are a resource to be mapped and monitored, our privacy and sovereignty meaningless on a galactic scale. And if the probe is a relic, it means that intelligence is transient, that civilizations, for all their achievements, ultimately die, and that the galaxy is a vast graveyard filled with the abandoned, still functioning toys of species that no longer exist. None of these possibilities is comforting, but let's also consider the alternative, the null hypothesis, that 3i Atlas is entirely natural. Even this raises profound philosophical questions, because if a natural object can be this strange, if it can exhibit this many bizarre properties and still be explained by the known laws of physics, then what will happen when we finally encounter something that is genuinely artificial? How will we know? How will we distinguish a supremely weird comet from a probe that has been perfectly designed to look like one? The ambiguity is maddening, but it is also instructive. It teaches us an essential lesson in cosmic humility. It reminds us that the universe is under no obligation to make itself clear to us, that mystery is the default state of existence, and that certainty is a luxury we are rarely granted. Here is a final thought experiment. Imagine you are the pilot of an interstellar probe, one of millions sent out by your civilization to conduct a galactic survey. Your prime directive is to observe without interference, to watch how civilizations develop on their own, untouched by outside influence. You enter the solar system. Your sensors immediately flag the third planet. You detect the chemical signatures of industrial civilization, the structured radio waves, the night-side glow of cities, the alteration of the atmosphere. You record it all, every detail, and store it in your vast memory banks. You complete your pre-programmed flyby, and you begin your exit burn, accelerating out of the system. As you depart, one of the planet's inhabitants, a curious astronomer, points a primitive optical telescope in your direction. They see a faint, moving speck. They wonder what you are. They speculate about your origin, your purpose. They feel a sense of awe and a profound loneliness. But you do not answer. You do not even notice their gaze. You just leave. Because from your perspective, this system, this planet, this species, is just one entry in a catalogue of millions. Not special, not unique, not central, just another stop. That is the perspective shift that 3i Atlas, in its silent, enigmatic passage, forces upon us. We are accustomed to thinking of ourselves as the observers, the explorers, the ones who catalogue the universe. But what if we are the ones being catalogued? What if we are an entry in someone else's database? And what if, after we are noted and filed away, the observer simply moves on, utterly uninterested in further contact? Is a humbling, even humiliating thought. But it might be closer to the truth than our egos would like to admit. The silence is the most haunting part of all of this. If 3i Atlas is artificial, it had every opportunity to signal us. It passed within a few tens of millions of kilometers of Earth, practically next door in cosmic terms. Any deliberate transmission would have been easily detectable. But it was silent, completely, utterly silent. It just moved through our home, did whatever it was programmed to do, and left. The silence could mean many things. It could mean we are not interesting. It could mean it operates under a strict non-interference directive. It could mean its communication systems are broken, or aimed in a different direction, or use a technology we can't perceive. Or it could mean the simplest, and for some, the most disappointing thing, that there is no intelligence behind it at all, just physics and chemistry, playing out in an intricate dance that only looks like purpose to pattern-seeking minds like ours. The existential stakes here are astronomical. If we are being visited by probes, by intelligences, by technologies we cannot comprehend, then the universe is a much more crowded, active, and complex place than we've dared to imagine. We are not alone. But we might as well be, because the others aren't talking to us. They're not helping us solve our problems. They're not threatening us with invasion. They're just passing through, indifferent to our triumphs and our tragedies, our loves and our wars. That is a loneliness that is, in some ways, deeper than being truly alone, because it means the cosmos is teeming with life and mind, and we are still isolated, still shouting into the void and hearing only the echo of our own voice. On the other hand, is natural. If all of this speculation is just us projecting our hopes and fears onto a random piece of cosmic driftwood, then we are alone in a different, more classic sense. We are the only ones asking these questions, the only ones building telescopes and spacecraft, the only ones trying to understand the universe. And that is both terrifying and inspiring. Terrifying because it means we are fragile, isolated, the only spark of consciousness in a cold and indifferent cosmos. Inspiring because it means our existence matters profoundly, that the questions we ask and the knowledge we gain might be the only light of understanding in a universe of darkness. Atlas does not answer these questions for us. It cannot. It just poses them, with its strange path and its anomalous behaviour and its refusal to fit into our comfortable categories. And that is precisely why it matters, why we spend so much time and resources tracking it, studying it, arguing about it. Because whether it is a comet, or a probe, or something beyond our current imagination, it is forcing us to confront the possibility that the universe is far stranger, far more wonderful, and far more mysterious than we know. And that confrontation, that moment of profound uncertainty, is where true science begins. It is where we grow. It is where we learn. It is where we push past the boundaries of what we think we understand and reach for something more. So, who or what is 3i Atlas looking for? Maybe it's not looking for anything. Maybe it's just drifting, following the laws of physics, bound by gravity and momentum and nothing else. Or maybe it's looking for something we can't imagine, for criteria we don't meet, for signatures we don't produce. Maybe it's looking for older, wiser civilizations. Maybe it's looking for ruins, for the remnants of species that came before us and failed. Maybe it's looking for resources, for raw materials, for data that has nothing to do with biology or intelligence. And unless we somehow find a way to intercept it, to catch up and look it in the eye, we may never know. But the question itself is valuable. It is perhaps the most valuable thing 3i Atlas has given us, because it forces us to think deeply about our place in the cosmos, about what we might mean to other intelligences, about whether we are the centre of the story or merely a footnote. And that kind of thinking, that willingness to stare into the abyss of our own insignificance, is essential for a species that is just beginning to take its first tentative steps beyond its cradle. We need humility. We need perspective. And 3i Atlas, silent and enigmatic as it is, offers us both in abundance. Now, let's zoom out from the philosophy and return to the practical. Let's look at what else has been happening, at the other observations and missions that are adding crucial context to this mystery. Because 3i Atlas is not an isolated event. It is part of a larger story unfolding right now in our solar system. A story about how we are learning to detect, track, and understand these silent visitors from the stars. On October 3, 2025, 3i Atlas made a relatively close pass by Mars. Not a nail-bitingly close approach, but near enough that the fleet of human-made machinery orbiting and roving on the red planet had, in theory, a ringside seat. And according to a dedicated group of amateur astronomers and image processors, they did. The claims are tentative, the evidence grainy and pushed to the absolute limits of detection. But if true, they represent something extraordinary. The first ever multi-planet observation of an interstellar object, a coordinated celestial surveillance operation spanning 2 worlds. The story begins with NASA's Perseverance rover, sitting silently in the dust of Jezero crater. Perseverance's mission is to search for signs of ancient Martian life, to drill into rocks, and to cache samples for a future return to Earth. It is not a comet hunter, but it has eyes. Its sophisticated Mast-Cam-Z camera system, mounted on a tall mast, can swivel and gaze at the sky. When 3i Atlas swept past Mars, a few sharp-eyed enthusiasts on Earth had a brilliant idea. Could Perseverance see it? Burns, an amateur astronomer with a talent for teasing signals from noise, thought it was possible. He began downloading the raw image data streamed back from Perseverance's Mast-Cam-Z. The comet would be an incredibly faint, fast-moving smudge against the background stars, far below the camera's design specifications for such a target. But Burns began stacking images, combining dozens of exposures to bring out faint details that would be invisible in any single frame. He aligned them, processed them, and according to his analysis, he found it. He produced a time-lapse sequence showing a faint, moving point of light, exactly where the orbital predictions said 3i Atlas should be. Another amateur, Simeon Schmaus, independently performed a similar analysis and came to the same conclusion. A faint object in the predicted position with the predicted motion. These observations have not been officially confirmed by NASA or any major scientific institution. The signal is at the very limit of what is detectable, and there is always the possibility of a digital artifact, a cosmic ray hit on the camera sensor, or a simple misidentification. But the amateur astronomy community is buzzing with excitement, because if Perseverance really did capture 3i Atlas, it means we have observations of this interstellar visitor from 2 planets at once. Earth-based telescopes were watching, the Hubble Space Telescope was watching, and now, potentially, a rover on the surface of Mars was watching too. Why is this such a big deal? Because in astronomy, geometry is power. When you observe an object from a single location, like Earth, you can measure its position and brightness, but you cannot directly measure its distance or its true three-dimensional motion through space. You have to infer those things from models and assumptions. But when you observe from two widely separated locations, in this case Earth and Mars, tens of millions of kilometers apart, you get the powerful tool of parallax. You can triangulate the object's position in space with immense precision. You can refine its trajectory to a degree that was previously impossible. You can check the orbital models for tiny discrepancies that might hint at non-gravitational forces or even deliberate maneuvers. The Mars observations, if confirmed, would have provided exactly that. A second vantage point, a different angle, a chance to see parts of the comet and its tail that were hidden from Earth's view. This is the kind of data that can turn a speculative model into a confirmed theory, or reveal entirely new mysteries we hadn't even considered. But beyond the raw data, the Martian flyby is a powerful proof of concept. It shows that we can use our existing planetary missions, spacecraft that weren't designed for hunting comets, as a distributed, solar system-wide surveillance network. Perseverance is on Mars to study rocks, but it can also look up. The ESA's Mars Express and Trace Gas Orbiter are there to study the atmosphere, but they too have cameras and spectrometers that can be repurposed. If we are clever, if we plan and coordinate, we can build an early warning system for interstellar visitors. Imagine if we had active missions at Jupiter, at Saturn, in the asteroid belt. Imagine spacecraft stationed at the stable Lagrange points, acting as permanent sentinels. If every major body in the solar system had at least one mission with the ability to point an instrument at the sky, we could track an object like 3I Atlas from the moment it entered the solar system to the moment it left, with continuous coverage, multiple viewing angles, and a flood of overlapping data. This isn't science fiction, it's a matter of coordination, will, and funding. The Mars flyby also raises a tantalizing, unanswerable question. Did 3I Atlas do anything unusual near Mars? Did it change its behaviour, release a burst of material, or make a tiny course correction that we couldn't detect from Earth? The Perseverance images, even if real, are just pictures. They don't have the resolution to see fine details. But they are a start. They open the door. The next interstellar visitor might pass even closer to Mars, or to a spacecraft orbiting Jupiter. We will be ready with better cameras, better software, and a better understanding of what to look for. There is a certain poetry to the idea that Mars, a world we are only just beginning to touch, served as a silent witness to an interstellar traveller. Two explorers, one human-made and rooted to the ground, the other of utterly unknown origin and fleeting as a shadow, sharing a moment in the vastness of space. Did Perseverance see it? We believe it might have, and if it did, it's a potent reminder that our ability to see the cosmos is growing, that our presence is expanding beyond Earth, and that every new mission we send out adds another set of eyes to watch for the unexpected. But Mars isn't the only robotic platform that might have caught a glimpse of 3I Atlas. Another, even more distant spacecraft might have had an even more unique view. Icy Moons Explorer, or JUICE, is one of the most ambitious missions ever launched by the European Space Agency. It left Earth in April 2023, and it is currently on a long, complex journey through the inner solar system, using gravity assists from Earth and Venus to fling itself toward the outer solar system. Its destination is Jupiter, where it is scheduled to arrive in July 2031. Its primary mission is to conduct detailed reconnaissance of Jupiter's large, icy moons, Ganymede, Callisto, and Europa, to probe their hidden subsurface oceans and assess their potential for harbouring life. Ilian's a comet-chasing mission, but like Perseverance on Mars, JUICE is a sophisticated scientific platform packed with a suite of powerful instruments, high-resolution cameras, spectrometers, magnetometers, and particle detectors. And as 3I Atlas emerged from its close pass by the Sun, reappearing from the glare of solar conjunction, JUICE, by sheer chance of orbital mechanics, may have been in a unique position to observe it. Solar conjunction is a perennial problem for astronomers on Earth. When an object in space passes too close to the Sun from our line of sight, it is lost in the overwhelming glare. Our telescopes cannot safely point that close to the Sun, and the object becomes unobservable for weeks or months. But a spacecraft in a different part of the solar system has a different perspective. What is hidden from Earth might be perfectly visible to it. Depending on its exact position in its long cruise phase, JUICE could have had a clear, unobstructed view of 3I Atlas during a time when we on Earth were completely blind. The specifics depend on precise orbital trajectories and whether the JUICE mission controllers had the foresight and the fuel to point its instruments in the right direction. But the possibility exists, and if JUICE did observe the comet, the data would be priceless. Its instruments could have measured the comet's composition directly, analysed the dust particles in its coma, mapped its magnetic field, if any, and monitored its activity with a sensitivity that Earth-based telescopes couldn't match. We venture into the realm of wild, thrilling speculation. What if JUICE detected something that wasn't just a comet? What if its particle detectors picked up an anomalous spray of charged particles, the kind that might be associated with a powered thruster? What if its magnetometer registered a faint, structured magnetic field that shouldn't be there around a simple ball of ice? What if its cameras captured a brief, inexplicable flash of light from the nucleus, or a plume of material that had the spectral signature of combustion rather than sublimation? These are low-probability scenarios, the stuff of science fiction. Almost certainly, if JUICE saw anything, it saw a comet behaving like a comet. But almost certainly is not definitely. And in the absence of publicly released data, speculation flourishes. The idea of a spacecraft detecting a technosignature, a measurable indicator of technology, is not new. SETI has searched for them for decades, but usually in the context of distant stars. The possibility that a technosignature could be right here in our solar system, passing through on a hyperbolic trajectory, is a game changer. It suggests that evidence of other intelligences isn't necessarily something we find across the light years. It could be something that comes to us, transient and silent, a ghost in our own celestial backyard. JUICE's potential, yet unconfirmed, observations also highlight a critical gap in our current approach. We do not have a single mission dedicated to intercepting interstellar objects. We rely on luck, on serendipity, on the chance that a mission built for another purpose will be in the right place at the right time and able to look in the right direction. This is a reactive, haphazard strategy. It means we are always behind, always trying to catch up to mysteries that are already receding into the distance. But that is changing. There are missions on the drawing board, proposals being funded, designed with the explicit purpose of chasing down these enigmatic visitors. And the most promising of them is called Comet Interceptor. A mission with a unique and brilliant premise. It is a spacecraft without a target. Scheduled for launch around 2029, it will not head directly to a known comet or asteroid. Instead, it will journey to a gravitationally stable parking orbit, a Lagrange point, and it will wait. It will wait in a state of readiness, monitoring the skies for the appearance of a new, pristine comet, one from the outer solar system, or better yet, from interstellar space. And when a suitable target is discovered, Comet Interceptor will wake up, fire its engines, and race to intercept it. The mission consists of a main mothership and two smaller, agile probes. All three are designed not to orbit or land, but to perform a high-speed fly-through of the comet's coma, the cloud of gas and dust surrounding the nucleus. As they zip past at incredible speeds, they will gather a torrent of data, high-resolution images of the nucleus, direct samples of the gas and dust, measurements of the magnetic and plasma environment. The beauty of this design is its flexibility and speed. Because it is already in space, waiting, it can respond to a new discovery within months, not the years it would take to design, build, and launch a new mission from scratch. This makes it the perfect tool for a visitor like 3I Atlas. The tragic irony is that Comet Interceptor came too late for 3I Atlas itself. By the time the mission is operational, 3I Atlas will be far beyond the reach of any current propulsion technology, a faint ghost receding into the galactic hinterlands. But the next interstellar visitor, the one we haven't found yet, could be its target. The challenges of such an interception are immense. Interstellar objects move fast, often at tens of kilometers per second. Matching their trajectory requires a huge amount of delta V, a change in velocity that demands powerful engines and a lot of fuel. The mission planning is a complex ballet of orbital mechanics, requiring precise timing and a deep understanding of the target's path. Communication is another hurdle. The data gathered during the brief, high-speed encounter has to be transmitted back to Earth across millions of kilometers, a process that can take hours or days, with no chance for a second pass. Constraint. In the outer solar system, where many of these intercepts would occur, sunlight is too weak for efficient solar power. The spacecraft would likely need nuclear power sources, like RTGs, which are expensive and politically complex to produce. But the missions are aware the probes will be lightweight and hyper-specialized, designed to gather a maximum amount of science data in a minimum amount of time during their fleeting encounter. If Comet Interceptor succeeds, if it manages to fly through the coma of a pristine interstellar object and return its data, it will revolutionize our understanding of these visitors. All our current knowledge comes from remote observations, from millions of kilometers away. We have never been up close. We have never touched one. Comet Interceptor would give us that first, intimate look. We could analyze the composition directly, not through the filter of spectroscopy. We could see the true shape and structure of the nucleus. We could search for the subtle signs that have fueled so much speculation about 3I Atlas. And if it found detected alloys or compounds that don't occur in nature? If its cameras revealed geometric shapes, or unnaturally smooth surfaces, or evidence of seams and joints? It would be the discovery of the millennium, an event that would fundamentally reshape humanity's view of its place in the universe. It would confirm that we are not alone, and that others have, in fact, come calling. But even if it finds nothing of the sort, even if it confirms that interstellar objects are just comets, weird, wonderful, but ultimately natural comets, that too would be a monumental achievement. It would allow us to finally close the book on the probe hypothesis for the majority of these objects, or at least to narrow the possibilities dramatically. It would tell us that the universe, while strange, is not quite as strange as we had dared to hope or fear. And in science, ruling out the wrong answers is just as important as confirming the right ones. Interceptor represents the future. It is a mission built for the unknown, for the surprises, for the objects that arrive without warning and challenge our assumptions. It is a sign that we are learning, that we are adapting, that we are building the tools to answer the profound questions that objects like 3I Atlas have raised. But we are not there yet. For now, we are still observers, watching from a distance. And one of the things we are watching for, hoping for, is a signal, a sign, a clue that 3I Atlas might have given us, something we almost missed, something that whispers the truth about what it really is. 2025, for a brief, intoxicating moment, it seemed like the mystery of 3I Atlas might be solved in the most dramatic way possible. Astronomers using the powerful Meerkat radio telescope array in South Africa announced a stunning discovery. They had detected radio emissions coming directly from the comet. The news spread through the scientific community and the public like wildfire. Radio waves from a comet? That was unprecedented, almost unthinkable. Comets glow in reflected sunlight and emit in the infrared. They don't typically broadcast in the radio part of the spectrum. This immediately sparked a frenzy of speculation. Was this it? Was 3I Atlas finally breaking its silence? Was it transmitting? Was it at long last revealing itself as an active technological object? Beared with the intoxicating possibility that we were witnessing the first confirmed technosignature, not from a distant star, but from an object right here in our solar system. It felt like the plot of a movie, the moment of first contact. But science, true science, does not run on excitement and speculation. It runs on cold, hard, verifiable evidence. And within days, the researchers who made the discovery published their full analysis. The radio emissions, they revealed, were not a message. They were not artificial. They were natural. The signal was identified as a specific emission line at 1665 MHz, a frequency associated with the hydroxyl radical. Hydroxyl radicals are simple molecules that form when water ice, H2O, is broken apart by ultraviolet radiation from the sun. These excited molecules then release photons at characteristic frequencies as they relax, and one of the strongest of these lines is in the radio band. What Meerkat had detected was not an alien broadcast, but the faint, natural radio whisper of water vapour being dissociated in the comet's coma. It was chemistry, not communication, physics, not philosophy. This episode is a perfect, almost textbook case study in the scientific method and how it distinguishes the extraordinary from the merely unusual. The initial detection was a genuine anomaly. Radio waves from a comet are weird, but instead of jumping to the most exciting conclusion, the researchers did their job. They analysed the signal's properties. They looked at its spectrum. They compared it to known natural phenomena, and they found a perfect, elegant, and completely natural explanation that fit the data without requiring any new physics or any appeals to intelligence. The lesson is clear and vital. Even when something looks, feels, and smells like it could be artificial, the first, second, and third steps are always to exhaust the natural explanations. And nature, as we are constantly reminded, is endlessly creative and full of surprises. The universe is under no obligation to conform to our expectations of what is normal. But here's the thing. The fact that 3I Atlas was emitting detectable radio waves at all, even natural ones, is a significant discovery in its own right. It reminds us of how much we still have to learn. We detected these hydroxyl emissions because we happened to point a powerful radio telescope at the comet. How many other comets, both from our own solar system and from interstellar space, have similar radio emissions that we've never noticed because we weren't looking in the right way? Our view of the cosmos is still myopic, filtered through our assumptions and our technological limitations. We are only just learning how to see. The hydroxyl story also underscores the immense challenge of the search for extraterrestrial intelligence, SETI. If we are ever to find a genuine techno-signature, we must first be able to recognize and eliminate all the countless natural mimics. Nature is the ultimate copycat. Pulsars, with their perfectly timed pulses, were initially dubbed LGM for Little Green Men. Fast radio bursts were profound mysteries that sparked theories of interstellar propulsion systems. Even the legendary WOW signal from 1977 remains unexplained, but the overwhelming consensus is that it was likely a natural, if rare, phenomenon. The cosmos is filled with signals, most of which are just the background static of a dynamic and violent universe. The hard part is recognizing the one signal that isn't. So, how will we know if we ever find something real? The honest answer is that we probably won't know for sure, not immediately. It would require multiple detections by independent observatories. It would require a signal that contains complex, structured information, or one that defies any and all natural explanations, no matter how creatively we apply them. It would require a level of proof so high that it would overcome the natural and healthy skepticism of the entire scientific community. And even then, we would be cautious, because the history of science is littered with the ghosts of false positives and mistaken discoveries. But this rigour, this disciplined caution, is what makes science reliable. It is what separates knowledge from wishful thinking, and it is the standard we must apply, relentlessly, to 3I Atlas. The anomalies are real, the questions are legitimate and profound, but we cannot assume it is artificial simply because we don't yet have a complete natural explanation. We must keep gathering data, keep refining our models, keep looking. And if, after all that, the anomalies not only remain but multiply. And if they all point consistently toward an artificial origin, then, and only then, can we begin to seriously entertain the possibility that we are not alone. Emission story is also a reminder that 3i Atlas is not done teaching us. Every time we look at it with a new instrument, in a new wavelength, we learn something unexpected. The mystery is not static. It evolves as our tools and our understanding improve. And that is what makes this so exciting. The data is not complete. The final chapter has not been written. There is still more to discover, more to debate, more to wonder about. That brings us to our final part, the synthesis of everything we have explored. What does 3i Atlas in its totality mean for us, for our understanding of the cosmos, for our future as a species curious enough to ask these questions? Through the data and the drama of 3i Atlas, we've navigated the precise arc of its trajectory, catalogued its 8 stubborn anomalies, delved into the natural explanations that almost fit, and dared to explore the speculative shores of the artificial hypothesis. We've confronted the philosophical abyss its silence creates, and tracked its passage past the robotic eyes of Mars. We've looked to the future, to interceptors and new ways of seeing. Now it is time to step back and ask the ultimate question. What have we learned from this enigmatic visitor, and what should we do now? 3i Atlas is a mirror. It reflects back at us our own assumptions, our biases, our deepest hopes, and our most primal fears about the universe and our place within it. For some, it is a comet, an extraordinary one to be sure, a statistical outlier, but a natural object nonetheless, a product of the chaotic and beautiful forces of interstellar chemistry and dynamics. For others, it is a probe, a silent, ancient, possibly orphaned artifact from another mind, a sign that we are not alone, but that we are also not particularly important. Both of these views are built upon the same foundation of data, the same observations, the same facts. The difference lies in how we interpret those facts, what weight we give to the cumulative anomalies, and our individual comfort with uncertainty. The scientific community is divided, and this division is not a weakness, it is a strength. Science thrives on this very tension, on competing hypotheses, on rigorous debate, on the constant friction between skeptical conservatism and open-minded speculation. The researchers championing natural explanations are doing essential work, building detailed models and refining our understanding of the physics that governs the cosmos. Those who entertain the artificial hypothesis are also doing essential work, pushing at the boundaries of convention and forcing us to consider possibilities that lie at the very edge of science. Both sides are necessary. The truth, whatever it may be, will eventually emerge from the crucible of this debate. But here is what we know for certain. 3i Atlas has irrevocably changed the conversation. Before its arrival, interstellar objects were celestial curiosities, interesting but not paradigm-shifting. Oumuamua sparked a brief firestorm of debate, but was largely dismissed as a weird but natural asteroid or comet. 2i Borisov was reassuringly conventional. 3i Atlas is different. It is too anomalous, too multifaceted in its strangeness to be easily dismissed or explained away. It forces us, as a global scientific community, to take the artificial hypothesis seriously, to give it a seat at the table, even if we ultimately vote against it. That, in itself, is a form of progress, because the next interstellar object, the one that comes after 3i Atlas, might not be ambiguous. It might be obvious. It might be broadcasting on all frequencies, or it might have a shape that is geometrically perfect. And if we haven't done the intellectual preparation, if we haven't practiced asking the hard questions and building the frameworks to analyse them, we will not be ready. 3i Atlas is our training ground. It is a drill for first contact. The forward look is both exhilarating and daunting. Missions like the upcoming Comet Interceptor, the data from JUICE, and the next generation of giant telescopes on Earth and in space will provide us with better tools, sharper eyes, and more sensitive ears. We are building a coordinated, solar system-wide sensor network capable of detecting and analysing these transient visitors in ways we can scarcely imagine today. The coming decades will see a revolution in our ability to study the strangers that pass through our celestial neighbourhood. With that revolution will come answers, or more likely, better, more refined questions. But we also need to start thinking seriously about what we will do if we ever find something that is unambiguously artificial. Do we have protocols? Plans? The answer, for the most part, is no. SETI has loose guidelines for how to respond to a signal from a distant star, but those assume the sender is light years away. They do not cover the scenario of a probe in our own solar system. If we confirm that an interstellar visitor is a technological artifact, we will be in utterly uncharted territory. We will need to decide, as a species, whether to attempt communication, whether to try to intercept it, whether to announce the discovery to the world immediately, or to keep it confidential until we understand more. These are not scientific questions. They are geopolitical, philosophical, and existential ones. We should be thinking about them now, before the moment of discovery arrives, and we are forced to decide in a state of panic and awe. There is also the broader cosmic implication. If interstellar objects are common, if they are passing through our solar system regularly, then the galaxy is far more interconnected than we thought. The theory of panspermia, that the seeds of life can be spread from star system to star by comets and asteroids, becomes more plausible. It is possible, though entirely unproven, that the very life we are made of was delivered to Earth billions of years ago by an interstellar traveller not so different from 3I Atlas. We could be the children of the stars, in a far more literal sense than we ever imagined. For there is the existential dimension, the one that 3I Atlas embodies so perfectly. This object, whether it is a comet or a probe, is a profound reminder of our own scale. The universe is vaster, older, and more indifferent than our egos can comfortably accept. We are not the centre of the story. We are not the pinnacle of creation. We are a young species on a small planet, trying to read the first few lines of a cosmic story that has been unfolding for billions of years before we existed. That is okay. In fact, it is liberating. Because the search for understanding, the relentless quest to know what is out there, is what makes us human. It is what drives us to build cathedrals of glass and metal on mountaintops, to fling our machines into the void, to ask questions that may have no answers. It is the one thing that gives our tiny, fleeting lives a connection to the immense and the eternal. So Atlas now. As we speak, it is out there, beyond the orbit of Mars, racing toward the outer darkness at 40 kilometers per second. In a few years, it will pass the orbit of Neptune. In a few decades, it will cross the heliopause, the final boundary where the sun's wind gives way to the interstellar medium. And then it will be gone. Truly gone. A silent speck adrift in the Milky Way, its trajectory carrying it toward, we know not what. Perhaps toward another star, another civilization, another moment of fleeting curiosity. Perhaps toward nothing at all, just the endless silent night between the galaxies. We'll never catch it. We will never know with absolute certainty what it. That is the very nature of exploration. We reach, we grasp, we learn what we can, and we accept that some mysteries are meant to remain mysteries, not as frustrations, but as inspirations, as reminders that the universe is still full of wonder. Atlas will fade from our telescopes. It will vanish from our instruments, but it will not fade from our imagination. It will remain there, a permanent question mark in the sky, a symbol of the unknown. It is a reminder that the cosmos is filled with visitors we do not understand, with paths we cannot follow, and with possibilities we dare not ignore. If it isn't here for us, then who is it looking for? Maybe it's looking for someone who has already found their answers. Maybe it's looking for someone who is still searching, just like us. Or maybe it's looking for no one at all. Maybe the question itself is the entire point. The question is what keeps us looking up. It is what keeps us building and searching and wondering. It is what defines us as a species born of stardust, cursed with consciousness and blessed with curiosity. Because in the end, whether Atlas is a comet or a probe, whether it is natural or artificial, whether it is ancient or ageless, it has given us a precious gift, a glimpse into the unknown. And in that glimpse, we see not just the universe as it is, but ourselves as we might become. Explorers, questioners, wanderers in the cosmic ocean, following the silent paths of those who came before, searching for meaning in the darkness, and finding, if nothing else, the courage to keep searching. The void is vast, the silence is profound, but somewhere out there, Atlas is still moving, still carrying its secrets, still tracing its lonely, perfect arc through the galaxy. And whether it was looking for us, for someone else, or for nothing at all, it has left us with the most important gift any mystery can offer, the reminder that there is always more to discover, always more to learn, always more to wonder about. And that wonder, that insatiable, burning curiosity about what lies beyond the next horizon, is what will carry us forward, long after 3i Atlas has disappeared into the cosmic night.